Who are these two people waiting?
There's a student and then there's the NVIDIA light.
Yeah. Can I start? Yeah, I think there's somebody waiting. We need to admit. It seems, I don't know, in YouTube channel I can see two waiting.
Oh no, sir. But once they start the laptop,
Oh, it started. Okay, thank you. There's somebody waiting. We need to admit. It seems, I don't know, in YouTube channel I can see two waiting.
once they start the laptop,
Oh, it started. Okay, thank you. It seems, I don't know, in YouTube channel I can see two waiting.
once they start the laptop.
So shall you wait for people to join or shall I? Of the classes covered till now. I were watching. In the chat box here, I will get okay. Anyway, okay. Good afternoon, all of you. The course Genome Editing and Engineering. So here I will be trying to address some of the concerns of the participants, if any. So let me start with the module that was discussed during week 7. So here we try to learn about the CRISPR-Cas9 technology and try to understand the CRISPR system in bacteria and how we use this CRISPR-Cas9 for genome editing. And we also try to find out various applications of this CRISPR-Cas9 technology and had a brief discussion on the various computational resources for CRISPR-Cas9. So those who have already attended the lectures now know what is CRISPR-Cas9 technology. That started with a discovery by Isino et al., who found that palindromic repeats in E. coli during alkaline phosphatase research. This was initially overlooked, but by 1992, it was identified by Francisco Mojica, who saw similar repeats in Halopherex. And although these were very interesting findings, it was difficult establishing its importance, particularly revealing its role in immunity, particularly in bacteria. So this CRISPR-Cas9 technology is a versatile and efficient genome editing tool, as you all know. This can be widely used in cells and organisms for various applications like disease modeling, gene therapy, in agriculture for improvement of crop varieties in bioprocessing, etc. Today, in the age of synthetic biology, genome editing actually is playing a very, very critical role. This technology employs guide RNAs, including natural crRNA, tracer RNA complexes, and the artificial sgRNA with linkers for chimeric cgRNAs for homology-directed repair, which enables genetic modification. There are other advanced applications like gene drives, which transmit edited genes at super Mendelian rates to control malaria mosquitoes, for example, and double-strand break-free techniques such as base and prime editing for safer edits. It also includes repurposed uses in gene regulation, epigenetics, chromatin imaging, and diagnostics, enhancing its utility across fields. So originally meant to edit genome at the base level, it has now found all these varied advanced applications, whereby today we can control the upregulation and downregulation of various genes. Apart from the wet laboratory techniques, we also discussed about the various computational tools that supports this CRISPR-Cas9 technology, particularly CRISPR Finder, ChopChop, and others. These aids helps in predicting CRISPR systems, designing guide RNAs, minimizing off-target effects. And these software tools underscore the evolution of CRISPR from a forgotten sequence to a revolutionary technology, broad scientific and medical applications. In module 8, in week 8, we try to learn about the applications of genome editing, particularly in treating human diseases like thalassemia, then severe combined immunodeficiency, and then hemophilia, which are some of the very, very important diseases found in the human population. We all know that thalassemia is an inherited blood disorder, which is caused by inefficient hemoglobin production, leading to dysfunctional red blood cells, anemia, and reduced oxygen delivery. This results in symptoms like shortness of breath, cold hands or feet, pale skin, fatigue, dark urine, and heart palpitations. So this is either classified as alpha or beta based on the deficient hemoglobin chain, which is alpha or beta. It is inherited in an autosomal recessive manner, differing from sickle cell anemia due to decreased synthesis rather than structural defects. It includes iron overload from transfusions, which damage the heart, liver, endocrine system vulnerability to infections, bone deformities, thicker skull, face bones, and an elder spin. So now with the availability of the power to edit the genome, its application has been tried, particularly with CRISPR-Cas9, for finding lasting cures for thalassemia. Then we have the severe combined immunodeficiency of the SCID disorder, which is a rare disorder from T-cell defects that impacts B and NK cells, leaving infants to prone to infections despite appearing healthy at birth. T-cells measure in the thymus using the TCI and APCs directly for antigen recognition. The B cell recognizes antigens directly and produce antibodies, also acting as APCs. The NK cells provide innate and anti-tumor viral defense via the IF and gamma. And occurrence is rare, 1:40,000 to 70,000 birds. This is linked to 18 genes. Example are the deficiency, IL-2 RG mutation for X-linked forms. Hemophilia is an inherited bleeding disorder from low protein factors 8 type A or 9 type B causing spontaneous bleeding, joint hemorrhages, and potential life-threatening issues. Then it affects around 400,000 people globally, with only 25% receiving adequate treatment. Particularly, hematorosis, 70 to 80% of the bleeds leads to hemophilic arthropathy, reducing joint morbidity and quality of life. This was first reported by Otto in 1803 with type A and B, distinguished by Pawlowski in 47. The term hemophilia was coined in 1828 by Friedrich Hoppe and Dr. Sloglin. So some of the common strategy in genome therapy is the use of CRISPR-Cas9 and other technologies prior to these, ZFN or TALENs, for the precise gene correction. So here we go for ex vivo editing of stem cells or in vivo delivery via viral and non-viral vectors. The advances in safety, specificity, and delivery systems are critical for clinical success of such therapies. We also discussed about the application of genome editing technologies in disease modeling, and we discussed about the models at various levels, and the organism level, the animal models, and at the cell level, the induced pluripotent stem cells. And then we had a discussion about the cancer disease models. So very often we create models of disease in animals because we cannot do testing in humans directly before animal testing. So here we try to replicate the human disease mechanism for studying pathophysiology and also gaining knowledge about the therapeutics. So you may have different type of models created, which may be spontaneous or induced. For the induced models, we go for chemical, radiation, viral or microinjection methods. And then today we have the power of genome editing at hand, which enables us precise creation of knockout and knock-in models mimicking human diseases. These mice dominate as models due to 85% gene similarity in humans, short generation time, and high reproducibility. But porcine models are also under development. And particularly, humanization of porcine models are one of the most important developments in the animal models creation. Then we have induced pluripotent stem cells, which are basically somatic cells that are reprogrammed using OSCAM factors, which are OCT4, SOX2, KLF4, and CMYC. And this convert the somatic cells into pluripotent state. And using these, we can develop disease models or apply them for regenerative therapy, drug testing, and thereby gain insights into personalized medicine. So in such cases, the genome editing technologies are getting integrated so that corrective mutations or that represents disease variants can be put into these models, particularly from patient-derived induced pluripotent stem cells. So we call as disease in a dish model because these cells can be grown in Petri plates or small culture tubes. With respect to cancer models, genome editing tools have been used to recreate cancer-specific mutations and translocations. And TALEN and CRISPR have enabled rapid in vivo tumor model generation for studying oncogene function and drug efficiency. The CRISPR-Cas9 efficiently induces chromosomal translocations and multi-gene mutations, advancing preclinical cancer research. Is there any questions raised? Let us check. Okay. Then there's module 10, where we have discussed about engineered immune cells for cancer therapy. So we had an overview of cancer therapy, which harnesses the immune system to fight tumors through approaches like immune checkpoint inhibitors, adoptive cell therapy, cytokine therapy, and cancer vaccines. And we had discussed about the tumor microenvironment, or TME, which comprises tumor, stromal, and immune cells that suppresses CTL and NK functions via cytokines and checkpoints. Then we discussed about immune evasion, where the tumor escape recognition by altering antigen presenting or presentation, inducing T cell exhaustion and metabolic suppression. We have also discussed about adoptive cell therapy that involves isolation, engineering, and reinfusion of immune cells such as TILs, TCR T cells, and CAR T cells. These CAR T cells are engineered with chimeric receptors for MSC independent recognition. Generations include co-stimulatory and cytokine modules for improved persistence and efficacy. Genome editing enables precise CAR insertion, removal of endogenous TCR-MS genes, and knockout of inhibitory genes to enhance anti-tumor activity and reduce toxicity. And these CAR T cells therapy shows success in blood cancers, but faces challenges in solid tumors, antigen escape, and cytokine release syndromes. We have also discussed about personalized therapy, starting with its history and basic concepts, and how genome editing is helping personalized therapy. The personalized or precision medicine tailors treatment to genetic, environmental, and lifestyle factors, replacing the one-size-fits-all approach. These roots can be actually traced to Ayurveda's Prakriti-based medicine, to modern pharmacogenomics and genome sequencing projects. So here, now the latest advances where CAR-T precision immunization using immune cell modification is possible. And then there are stem cell engineering, where iPSCs for disease modeling, gene correction, and regenerative therapy are being attempted. Then there are smart biomaterials and polymers for personalized drug delivery, implants and organ-on-chip models for precision diagnostics and therapy. Then we have concepts like theranostics, where we combine both the diagnostics and therapeutics for targeted disease management. In this context, the genome editing tools are used for targeted correction or disruption of disease genes. And CRISPR-Cas9 technology has enabled mutation correction, T cell engineering like PD-1 knockout, and high throughput drug target screening. And this has been applied in cancer, cardiovascular, infectious diseases, and clinical trials for genome-edited therapies. And their applications are expanding day by day. So we have seen large possibilities or huge possibilities of genome editing in creating animal models of diseases relevant to humans, as well as developing various therapies, including iPSCs, CAR T cells, and so on, which we just discussed. But while being excited about the possibilities of genome editing in human disease management, we have to be aware about the various ethical issues related to this technology, particularly the germline gene editing issues. So we have to be aware about the two things. One is the bioethics, and then second is the biosafety and what are the regulatory issues in genome editing. In many countries, there are now established regulatory guidelines and laws which regulate these technologies, while in others, it is still evolving. So as a researcher, we have to be aware of all these regulatory landscape globally. So we started with some of the basic concepts of bioethics, which originated with Fritz Zahar and evolved through the Nuremberg Code, the Declaration of Helsinki and Essilormer Conference, defining global standards for ethical biomedical research. Then we had discussed about the safety informed consent from participants, the justice and equity and transparency. Germline editing is highly controversial because heritable changes raise moral, legal, and societal questions. Now with the power of CRISPR-Cas9 technology, we can manipulate both the somatic and germline cells quite at ease. And there have been imaginary stories about the possibilities of designer babies, and which are actually possible. And so we have to be very, very alert about the bioethics as well as the biosafety concerns over here. So some of the ethical issues in germline editing involves safety risks like off-target effects. In spite of the precision of this technology being increased from ZFN through TALEN to CRISPR-Cas9 and also the ease of doing things, the off-target effects are still an issue of concern. And there may be also issues like mosaicism, where the coexistence of transformed and non-transformed cells will create this mosaic, and then unpredictable outcomes, because our knowledge, although it has advanced, are still limited in certain areas. Then there has been a dilemma regarding the consent. The embryos and future generations cannot consent because in certain nations, testing on embryos up to few days or a particular week is allowed, but we cannot take consent from embryos. But in this case, there are certain waivers, like the embryos are not considered to be legal entities. But this is not universally the truth. So we have to be very, very careful regarding the place and the country where these experiments are getting carried out. And there's also issue of equity, where the risk of genetic class divide and enhancement misuse may occur, and the moral status of the embryo, these differ globally because of various perspectives. Then there's a governance principle, which focuses on the promoting well-being, fairness, responsible science, and global cooperation. So in the US, this is when it comes to a regulatory landscape, it's mostly product-based, FDA, USDA oversight, and there is a focus on the somatic. In India, there is a GEAC and ICMR guidelines where germline editing is prohibited. In China and Japan, rapid progress but trigger post He Jiankui rules. So He Jiankui is one of the infamous scientists who edited the embryo to create AIDS-free babies or AIDS-resistant babies. That has been discussed in the lecture earlier. And then in European Union and Africa, their approach has been cautious, and they have adapted to process-based regulation. In Australia and Canada, they go by case-by-case GNA, GMO approach governance. So with this, we sum up the various modules from week 7 to week 12. So, and if there are any questions, we can take up those questions. Yeah.
One of the participants has raised his hand.
Yeah. So, Syed Sabur Siddiq. Yeah. Syed, please come in. Syed, can you come in? What's your question? I can see he's raising the hand, but easy online. Syed. No. Syed, can you? You are not audible. We cannot hear him, right? He's writing. Syed. Why is not audible? He's audible in YouTube?
No.
Syed, you can type your query.
Also, we can stop sharing.
No, let it be. Okay, you can stop sharing. How do you stop sharing?
Sorry.
Okay. Oh, he's typing. Okay. What is the YouTube channel? Yeah. He's typing, but it's not.
So the question is this.
Yes. Yes, you are correct. If you have a monogenic disease, it is quite easy because we need to only deal with one gene. Then a polygenic disease. What is this?
So is it possible to create a disease model as close to human as animals?
Yeah, I get your question. Is it possible to create humanized disease model as close to human Alzheimer's? Yeah. So in principle, basically, we have to first understand what is humanization of an organism. So we try to, make the genes sequence similar to the human gene sequence. So if we know the various genes which are involved in the development of a disease, and we take this model as more of a network model rather than a single gene controlling a particular disease trait. So if multiple genes are involved and there is a network which finally is responsible for creating the disease trait. So with the power of gene editing, it is possible. We can go for multiple editing and change the sequences of these genes to be more human-like. So these are all technically possible. Any other questions? No. Oh, regarding your internship, yeah, I think you have mailed it. I will get back to you. So I will get back to you. So maybe it will be possible in December for short term, and in June, July for long term. I will get back to you. Yeah. Yeah, this is a separate issue. I will get back to your email and send you some instruction regarding this opportunity. Any other queries? Okay, thank you. Any other queries? No. No, sir. Small meeting. Yeah, there are some models available, mouse models available for Alzheimer's as of now. So we will send you those additional information so you can go through them. So those things we can mail you separately if you want to have an in-depth study about some of the mouse models in Alzheimer's disease. You want some information on the humanized Alzheimer's disease models. So we'll find out the information and we'll send it to you.
Is left the chat. Is left the chat.
Is left the chat. Any other queries? No.
No, sir.
So as there are no other queries, so we stop here for today. So thank you for your participation.